This is our introduction to gases. We're going to talk about the properties of gases. We're going to talk about the units that come with those properties. Let's start by talking about why gases get their own entire chapter. And we're going to compare gases to solids and liquids. Let's start with something we're a little bit more familiar with. We're going to start with the solids here. Solids have really strong intermolecular forces, and that might not be a word that you've heard before, but intermolecular forces means the attractive forces between particles. And that's something that we're going to get to in a later chapter. But if the intermolecular forces are strong, the particles want to hold together, and in this case, the particles are kind of held in place. That means that gases are the most dense of states. The particles can't really move a whole lot. They're really only wiggling in place like a vibration. Now let's compare that to the kinetic energy of the particles. We say that the intermolecular forces are stronger than the kinetic energy. That means that the kinetic energy that they have, which all moving particles have, is not as strong as the attractive forces between the particles. And that's important because even though they have kinetic energy, the attractive forces are stronger, and so the molecules or the particles are held in place. When we compare that to gases, gases have huge kinetic energy compared to the intermolecular forces. What that means is that their kinetic energy is large compared to the attractive forces between the particles. The attractive forces between the particles are almost entirely negligible in gases. It's almost like they don't feel the presence of any other gas particle. And because of that, the gases are able to move freely, they're pretty far apart from each other, and we pretty much say they have no attractive forces. Now that makes gases really different from solids. The particles are moving freely instead of just being able to kind of wiggle in place. There's a lot of space between the particles, unlike solids where the particles are really close together. And so gases are completely different than solids in almost all of their physical properties. Now somewhere in between are liquids. Liquids have attractive forces and some kinetic energy, so that allows for some movement. The molecules or compounds or particles can kind of tumble over each other. It means that liquids are going to be more dense than gases, but less dense than solids. So liquids are kind of like the in-between stage between solids and gases. Now back when we talked about physical properties, we talked about how we can take a solid and make it into a liquid, and we can make that into a gas. And there are some words that are associated with that. So when we're going from a solid to a liquid, we call that melting. And we consider it to be endothermic because we have to put energy in to make that happen. When we take a liquid and we keep on heating it until it turns into a gas, in kind of real life we call that boiling. In chemistry we call it vaporization. And that is also endothermic. Okay, going back the opposite way, if we're going from a gas and cooling it down until it turns into a liquid, we call that condensation. And since we're cooling it down, we're getting the energy back. So that's actually an exothermic process. The gas is exothermic. Whatever it's giving its energy to is endothermic. So the gas is exothermic, the surroundings are endothermic. If we go from a liquid down to a solid, this is what we call freezing. And that is also exothermic. Okay, the fun ones are on this side. Going from a solid all the way to a gas is called sublimation. And that doesn't happen for a lot of compounds, but we're eventually going to get to the reasons why some compounds sublimate and other ones don't. Anytime we're putting energy in, that's going to be an endothermic process. And then going the opposite way, so we're going down this way, we call that deposition, because a gas deposits itself as a solid on a wall, like we usually call that a cold finger, but we call it deposition when the process happens, and that is an exothermic process. Now, because this chapter is about gases, we're going to be talking about vaporization. We're going to be talking about condensation. We might be talking about sublimation and deposition. Let's talk about some other properties of a gas, how we describe a gas. Gas particles can kind of be like if you imagine a billiards table and the balls are kind of bouncing around on this table, hitting the walls and hitting each other. That's kind of the way gas particles move in a container. Now, when we say gases are constantly bouncing around and hitting each other and hitting the walls, that is technically the kinetic molecular theory of gases. And we'll break down those words. Kinetic means the energy of motion. So we're saying that the gases are constantly in motion. Here we have molecular. That means that we're going to see the gases as mostly molecules. If you're wondering what the other options are, we could also think about ionized gases, so gases that have charge on them. We don't want to do that right away. We want to keep things simple. When things have charges, things get a little bit complicated, so we're going to keep things as neutral molecules. And when we put those together, we're talking about how gases are moving in a container with each other, and the kinetic molecular theory of gases tells us how we think gases will behave. Now, this is the kinetic molecular theory of gases. I'm going to kind of go through these and explain why some of them are important. Some of them might be obvious to you, others might not be so much. So we are going to say that gases consist of molecules that are in continuous random motion. That means they're always moving. And random motion, that's important. If they were ions, the motion wouldn't be random. They would be positives and negatives, would be attracting each other in certain directions. But we're not going to look at gases like that. So we're going to be able to see gases moving in random motion. The next one is the volume of gas molecules is negligible in comparison with the total volume in which the gas is contained. Now, if that doesn't make sense to you, I want you to think about how gas particles have a lot of space between them. So this is my container with gas in it. And what we're saying there is that the volume of the gas particles or gas molecules is negligible in comparison with the total volume in which the gas is contained. So this is the total volume in which the gas is contained. And I'm just going to rewrite that. Okay. And what I'm going to do is I'm going to stack those same gas particles, but all together in the bottom. So like this is, they were, okay. Now that little tiny volume there is very small compared to this entire volume. And the reason why we can say that that's true is because gas particles themselves are small and they have a lot of empty space between them. So when they spread out to fill an entire container, most of that is empty space. Why that's important to us is because it means that gases are going to be extremely compressible. And that's going to be one of the things that we can use to do some calculations in the future. Okay, number 3 says that the attractive and repulsive forces between gas molecules is negligible. We can say that that's true for 2 reasons. 1, none of the gas particles are charged. And 2, they are so far apart from each other that even if they were attracted to each other, they couldn't feel it. It's kind of like we know magnets can be attracted to each other, but if you keep one in one room and one in the other, they don't pull each other barely at all. So that's the way that we see gas particles behaving. Okay, this is a big one. The average kinetic energy is constant as long as temperature remains unchanged. What we're saying there is that when gas particles hit the wall, so this is my gas particle, and it hits the wall and it bounces off, the amount of energy that it gives the wall is so small compared to the kinetic energy that it has that it's almost like it doesn't lose any at all. Okay, so I'm not saying that it technically doesn't lose any. I'm saying that with the number of sig figs that we can measure, this little amount of energy that it gives the wall is negligible, so small compared to the kinetic energy that it's like it didn't even matter. Now that means that we consider collisions to be totally elastic, so the amount of energy that it has going in is same as the amount of energy going out. And that means that the pressure and the kinetic energy are going to remain constant unless we let gas out of a container. That's the only way that we're going to lose gas or lose energy or lose pressure. And the last one is that the average kinetic energy is proportional to the absolute temperature, and it says specifically in Kelvin. So this means that the kinetic energy of a gas will rise with temperature and decrease with if you lower the temperature, but only if you do it in degrees Kelvin. This is going to be very important for our calculations because a lot of times on our thermometers we measure in degrees C, but all our gas law calculations have to be in Kelvin before we even start them. So anytime you're given a degree C temperature measurement, you're going to convert it to Kelvin right away, and then you can do calculations with that. Now these 5 things are the things that describe gases, kind of how we see them on planet Earth, and these 5 things describe what we call an ideal gas. An ideal gas is a gas that behaves all the assumptions of the kinetic molecular theory. That means that it goes by those 5 characteristics. All gases can behave somewhat differently than predicted by the kinetic molecular theory, but it happens mostly at high pressures or at very low temperatures. And what I mean by that, so by very high pressures, I mean something like what's happening in the sun, or maybe on planet Earth, the pressures that we can create with a volcano, or that are naturally created with a volcano. For very low temperatures, I'm talking about close to 0 degrees Kelvin, so that would be something like out in space. Now, none of those situations are situations that we deal with very often. So we say that most real gases display nearly ideal behavior under normal conditions. And I'm going to say normal conditions are pretty much anywhere a human lives. Okay, we will talk about what happens when the assumptions don't work. We call that non-ideal behavior. And that happens under situations like those high pressures and those low temperatures, but we'll talk about that in a video later on. I'd like to talk about some specific numbers that we use to describe gases, and these are going to be considered like our gas law variables. Let's talk about them one at a time. The first one is volume. That's how much room a gas takes up, and we know, because of the kinetic molecular theory of gases, that if we give gases a small container, they will spread out to fill that entire container. But if we increase the size of the container, they don't just stay in that same area. They actually move and expand to take up all the space in the container. So the volume of the container is what we consider the volume of a gas. The pressure is sometimes kind of hard to imagine. We consider it to be the additive force exerted by all the gas particles. So if you can imagine a gas container like this, the pressure is, so if these are particles and they're hitting the wall like this, the pressure is all of these little forces added up. And so it is a force, and it also takes into consideration the overall space that force is being exerted on. This one might be a little bit easier. The amount, when we're talking about the amount of gas, we're always going to be talking about moles. So if you're given anything other than moles, like if you're given grams, you'll need to convert to moles. We know how to do that. We use the molar mass. The last one is temperature. This one's really important because it's proportional to the kinetic energy of the gas. We know if the temperature goes up, the kinetic energy also goes up. So this is actually, the higher the temperature, the more the molecules are moving, the faster the molecules are moving. When we start doing calculations, we're going to see these variables labeled in a way. For volume, we're going to use V. For pressure, we're going to use P. For the amount, which is the moles of gas, we don't get to use M because that usually has to do with mass, and we're not going to use a capital M because that has to do with molarity, so we don't get to use those. Usually for the amount of gas, it's labeled as N, so N is the moles of gas, and temperature is going to be T. When we talk about units, we're going to need to keep track of units as we go through our calculations. For volume, we're going to just use kind of normal volume units like liters and milliliters. Those are fine. For pressure, you're going to see units like ATM, which is atmospheres. You're going to see PSI, which is pounds per square inch. And that's pretty common in the US, especially like your tires are labeled as a certain PSI. The next unit for pressure is torr. That's short for Torricelli. That's just a guy who studied gases. And the last one is millimeters of mercury. We'll talk about converting about those units in a minute. The amount, we're always going to use moles, like we said before. And for temperature, we need to do all our calculations in Kelvin. So remember, if you're given degrees C, you're going to convert to Kelvin before you do your calculations. If you're given Fahrenheit, you'll convert to Kelvin also. Right. It's been a little while since we did some math, so I thought it'd be a good idea for us to practice some temperature conversions and then talk about pressure and talk about some pressure conversions too. Okay. Most of our thermometers read in degrees Celsius, so it's going to be important for us to be able to do Celsius to Kelvin conversions. This one is converting 25 degrees Celsius to Kelvin, and to do that we add 273.15 to it. This. And I just want to remind you about our sig-fig rules. When we're doing addition and subtraction, our answer can't have more places past the decimal than our measurement with the least places past the decimal. So we're going to look for the least places past the decimal. This one only has 1 place past the decimal. This one has 2. So the top one has less places past the decimal. That means that our answer can only be to the ones place, which matches the one with least places past the decimal. So if we cut it off there, we want to round to the place that this 1 is, and because of the odd-even rounding rule, it means we're going to round up so that that would be an even number. So it's 298.2 Kelvin. All right, let's practice going the opposite way. Let's convert Kelvin to Celsius. You would need to do this if you did some calculations and you found Kelvin, but the question wanted you to write the answer in Celsius. So to do this, I'm going to do the subtraction, and I got 49.85 on my calculator. And when I'm figuring out sig figs, I want to round my answer to the least places past the decimal. But if you notice here, this one doesn't even have, my top one doesn't even have any places past the decimal. So I just kind of want to reword the rule that we use for significant digits. Really what we say is, when we're saying least places past the decimal, is if you underline the last sig fig in each measurement, we're picking the sig fig that is the furthest to the left. So my choices are either to pick this guy here or this guy here. I'm picking the one furthest to the left. That's the ones place. I'm going to round this to the ones place. And I'm going to round up in this case because the 8 is more than 5. And I would put a 50 like this. Now I have to put that decimal point there because if I don't and I just write it 50, I am rounding to the tens place, and that's not what I want to do. I want to round to the ones place, and the way to make that 0 significant is to put a decimal point there. also want to practice with some pressure conversions, but I also want to talk about what pressure means a little bit more, so maybe that can help us with our units a little. When we think about what pressure means, if you can imagine your hand, so this is your hand, and if you can imagine on the back of your hand, there is a 1 inch by 1 inch area. So 1 inch by 1 inch. Okay, so kind of imagine that on the back of your hand. Now what we're going to imagine is there are gas particles pushing down on that square inch of your hand. And you don't think about it, but on that area, that 1 square inch, so over 1 square inch, we actually measure about 14.7 pounds of pressure. So there's 14.7, almost 15 pounds of pressure on that square inch of your hand. Now imagine that over the entire area, over your hand, everywhere on your body, the atmosphere around you is pushing in on you at 14.7 pounds per square inch. The reason why you don't feel like you're being squished is because the stuff that's on the inside of you, all your muscles and your blood and everything, are pushing out with 14.7 pounds per square inch. So in this slide, I have a bunch of pressure units on this side, okay? I have their abbreviations here, and I have their values at the same point. So at sea level, we're being pushed in on our bodies. The atmosphere around us is pushing in at 14.7 pounds per square inch. Now that's the same thing as 760 millimeters of mercury of pressure, and that's the same as 760 torr, and the same as this many pascals, and the same as 1 atmosphere. So these are all equal to each other. They're equivalent. Maybe a way that would feel a little bit better writing this is that 14.7 psi is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 1 atmosphere. I skipped over the pascals there just because it's a little less common. These are the ones that we're going to see the most often. So these are the most common ones. Now when you're taking your notes, this one is written to 3 sig figs, and this one's only written to 1 sig fig, and these are written to 2 sig figs. I'd like to clarify that a little bit. So what I'm going to do is I'm going to write it a little bit more clearly down here at the bottom. These are actually, should all have been written to 3 significant figures. So the way I'd like that to be written is actually 14.7 psi is equal to 760 millimeters of mercury, 760 torr. So that'll give it 3 sig figs, and that should be 1.00 atmospheres. All right, let's practice a little bit with some pressure conversions. Let's convert 785 torr to atmospheres. Okay, so to do that, we'd have to look up the equivalent. You can look back on that last slide. It's 760 to 1 atmosphere. So when you do that, you get 1.032 atmospheres. When we're talking about sig figs, this has 3, this has 3. I'm going to round that to 3 to get 1.03 atmospheres. Okay, let's maybe do one that's a little bit different. We'll go to atmospheres again, but we'll do kilopascals. Okay, so that's a kilopascal is 1,000 pascals, and we're going to go to atmospheres again. So the setup, very similar, kilopascals. I'm trying to get to atmospheres, and to do that, I looked up the equivalents, and I can only find the one from pascals to atmospheres. but I do know that 1 kilopascal is 1,000 pascals. And then there's 1.01325 pascals per atmosphere. I just got that on the last slide. All right, so units, Pascal, kilopascals with kilopascals, pascals with pascals, and I get atmospheres. And on my calculator, it gave me 1,003.7 atmospheres. For sig figs, this has 4. That's a definition. This has 1, 2, 3, 4, 5, 6, a lot. Okay, so I'm going to round this to 4. Sig figs, that'd be 1,004 atmospheres. I just wanted to go back to this slide for a second because the pressure units have always been kind of weird to me, and I wanted to talk a little bit about that. The pounds per square inch, that's the one that makes kind of the most sense to me. It's how much force is being pushed down on 1 square inch. So that I can kind of imagine what that means. But the millimeters of mercury seems weird to me, like we're measuring a force by a distance of a liquid. That one seems kind of crazy to me. So I want to talk about that one a little bit. I do want to mention that this idea of torr, you notice that these two numbers are the same. That's because Torricelli just wanted a unit named after himself. So he took millimeters of mercury and he said millimeters of mercury, I'm just going to call that a Torricelli. So if you get famous in science, you can name a unit after yourself. And then for once, the scientists made a nice tidy unit. We say that the pressure that we feel at sea level, okay, so the pressure that we feel on our bodies at sea level is just 1 atmosphere. That seems like a really nice number. We're going to be using atmospheres in a lot of our calculations. All right, so let's talk about how we can measure a pressure in a distance of a liquid. Okay, so I skipped back to the slides that we were going to before, and I want to look at this thing called a barometer. A barometer measures atmospheric pressure, so it measures the pressure that the atmosphere is exerting. And the way a barometer works is it has a pool of mercury down here, so it's like a little cup of mercury, and that cup of mercury has this tube, so that's this tube, down, kind of stuck in it. So it's an evacuated tube and it's stuck down into the pool of mercury. And what's happening is the atmosphere is pushing down on this pool of mercury. The pool of mercury is pushing mercury up into the tube. And so the harder the atmosphere pushes, the further the mercury goes up into the tube. So the distance that we measure of mercury is actually proportional to how the atmosphere is pushing down. So the higher the atmospheric pressure, the higher this column of mercury. Right, you guys might not have noticed, but we actually have had a barometer in our lab room the entire time. It's actually in our weigh room. Kind of in between the balances, it looks like a giant thermometer on the wall. And when we need to make pressure readings for the atmosphere, we go to that barometer and we read the atmospheric pressure. All right, so that's our video about gas characteristics. And we talked about pressure, we talked about volume, we talked about temperature, and we talked about units and converting with sig figs, as always.